last class, we were talking about how to accept or not to accept a language. So first, I would like to show you several ways of functioning for these machines. So let's suppose we have a string like this. And we have this machine. Now I want to ask you, can we say that in this configuration, can we say that when the machine halts, this string is accepted?
What is holds? Holds is when I don't know. Is the state the last state?
Yes.
Okay.
The halting state. It stops.
Okay. The stop state. Okay.
It's not accepted.
Yeah, it's not accepted. Why? Because what will happen? We start here analyzing. Now the head moves to the right. This is the first thing that is done. Then, as long as it finds an X, it will move to the right. And then again, we'll find an X and then move to the right. And then here, because we have a Y, we will stop. So yes, this machine stops. However, the second condition for accepting a string is not accomplished, is not complied. Why? Because sorry. This is not accomplished because we have not finished reading this string. We are stopping our processing here in this part. Actually, maybe we have just read the Y, and maybe we can say we have just finished up reading here. However, there are two conditions to accept a string. This is very important. To accept a string with a Turing machine. The first one is reach a halt state. Or not a, but the, because you can say there is only one, the halting state, and two, having read the whole string. Yes, so in this case, we are not complying with the second condition. That's why we cannot accept this string. So let's see another machine, another string. Let's suppose we have something like X, Y, something like this, and then we have a machine that says, no matter what it comes, X or Y. So the same question, can we say, is the string XY, XXY accepted by this machine?
Yes.
Yes, because we are reaching the halting state after analyzing the string, and also we have read all the whole string. If we see is on tape like this, we will have the first movement is to the right, so we'll move our head to the right, and then whenever we find an X or a Y, we will just keep moving to the right, and when we have a Y, then we move to the right, we have an X, we move to the right, we have another X, then we move to the right, and we have a Y, and finally we move to the right. The machine will stop in this state or in this position of the tape because we are not saying what will happen when we reach a blank symbol. It's as if it was implicit, something like this, like with a blank symbol, halt. But we never represent the halt states in this machine, okay? We just don't put anything in it, and it means it will just stop.
Se lo pides a Mauricio, ¿verdad? Para escribirle por Telegram.
So the two conditions are complied. We reach the halting state and we have read the whole string. This is very important. And what happens with other machines, like the one we have been studying for several times? We have used, let me copy and paste again. And I will explain this again as well, because this is very important. I'm pasting from the book. So we have been studying this machine for several times, and we have found that this machine destroys the string. We start with something like this, X, X, Y, Y, Z, Z, and then we will start looking for an X and then for a Y and a Z. And in the process of looking for them, we are eliminating them. We are destroying them. How? Because we are doing a shift left for each X, a shift left for each Y, and a shift left for each Z. So then we go back, we at the beginning put a marker here, we go back to this marker and again start the sequence of looking for an X, a Y, and a Z. And at the end, because all this was destroyed, we assume that we should be on a hash symbol. If this is not the case, it means there is something else. Supposing we have X, X, Y, Y, and Z, Z, and again an X. Then we destroyed this X, Y, and Z, X, Y, and Z, and then we are not finding this hash because we are having something else, meaning that the string was not completely processed. So in this case, whenever we reach the halt state, which goes out at this part, this is implicit. It means if you find the hash, then halt. This is implicit. We have read the whole string. Also, we have destroyed it. We have completely parsed it. So we say that the two conditions are met. The first one, the whole string is analyzed, and also we reach a halt state. And also remember that not all Turing machines are designed for accepting or not a string, because let's suppose you have some kind of machines like write an X, move to the right, and then write an X and move to the right. So this machine is not designed for accepting or not a language. It's designed for adding a lot of X's. Or let's do another interesting machine. What if we want a Turing machine that copies a string? I think that was one of the exercises you did, or you did a very similar one. I think you did the one that wrote the string the reverse way. So let's do it the normal way. We have something like x, y, x, x, y, and we want to copy here. We want to copy this into that place, and we don't know what else is over there, and then our head is positioned over there. How to design this machine? Well, first we need to know that usually the first operation is moving to the right. Then we know this will be here. And then we will have different symbols on the tape. We can use, as you can recall, that if we find an X or a Y, we can use it as omega, meaning that if we found an X or a Y, it will be represented as an omega. Also remember that this is not a variable, because there is no way to store variables. This is just a diagram shortcut, as we saw last time. And we can rewrite the same Turing machine without using this mechanism. However, it is convenient for us to use this mechanism to simplify our diagram. So this is just a mechanism to simplify diagrams. It does not mean that really there is some set of registers, for example, where we store our temporary variables for the Turing machine. No, it's not the case. Okay, having clarified this, then we have read this X and Y. And what do we need to do now? We need to move to this position. Why? Because we will write here at this part, this character. So meaning that we will move to the right until we find a blank space. And we have a soft machine for doing so. This is move to the right until you find a blank space. At this point, we will just erase this, and then we are positioned at this part, and we'll move just one character to the right, meaning that we are here. And at this point, we will write omega, correct? Because we are, this is exactly the same character we have seen before, X or Y. This is represented by our omega. Once we have done this, the string will be like this. We have written X here. We need to go back then. For doing so, we need to go back first by finding the first blank space. Now we will go to the left to find the first blank space. And then we need to move to the second blank space to the left, which is this one. So for this purpose, we write again left and right until we find the left space, the second space to the left. And now that we are here, we forgot to do something very important, without which our machine won't work properly. And this is that we forgot to mark what was the character that needed to be replaced, right? So we forgot to say, oh, this is the X. I have already copied this symbol. So for this, I need to go back. Sorry, I forgot about it, but it's usually the way you will be doing when you are designing some machines. So at this point, what we had to do before, when I read this X, I should have destroyed it, maybe by using an asterisk or something like this. So let's say I destroyed it and put an asterisk on it. So instead of going back and looking for this blank space, we would look back for this asterisk, right? So, and this asterisk will be written just right after we found this. So here. Okay. So let's recap this in order not to confound you. Let's go back and try to execute so far this machine. So let's go back and let's suppose we haven't done anything. We will start over again. We have here a blank space and more blank spaces indefinitely. Here. Okay, then the first thing we do is move to the right. Moving to the right means going here. At this point, we will find an X or a Y, and then we will find omega. this omega represents X in this case. Omega is X. At this point, we write an asterisk. Then this X is destroyed with an asterisk. And then we move to the right until we find a blank space, meaning our head will move to this point. Then we will move one cell more to the right. We will be here at this point, and then we will write omega at this point. Sorry. Oh, sorry, I have to take a call. Bueno. Bueno. Sí, dígame. Sí, muy bien, gracias. Estoy en una reunión. Perdone. Sí, gracias. Sorry for the interruption. It was GoDaddy. I don't know what do they want. Okay, so can you hear me properly?
Yes.
Okay, thank you. So we were here at this point. We found omega. Omega is X. Then we are positioned at this part. Then we replace this with omega here. We will erase this and then write, of course, not omega, but the value of omega, which is X. And then we move to the left, finding the first blank space, which is this one. And then move to the left to find the first asterisk we find, meaning that we will stop here. At this point, we continue our processing. We will write again omega, thus reconstructing the former X we had here. And then we need to move to the right and begin the whole process again. Once we wrote this, then it will go and move to this part, regardless of what we find, but usually we can say it should be an X or a Y. Meaning here we have just written this omega, so we are sure it should be an X or a Y because omega cannot be anything else. That is why we can erase this, and it means whatever you find there, you just go back and then move to the right. And moving to the right, we'll do this. Continuing the operation, I think this Turing machine is almost ready. You will have a Y, and now omega is Y. And then we replace this by an asterisk. Then move to the right until we find the first blank space, and then move again to the right. Okay, then we see we have a problem here because we move to the right here, and then at this point we will write omega, thus incorrectly erasing the previous X we have seen with a Y. So this is wrong. You see, I'm doing this because I want you to see the process of constructing this machine that is like sometimes trial and error, because you are seeing what happens when you don't consider something that can happen. Okay, then at this point you see, well, no, then the problem is with this R, because then we need to move not just to one to the right, because we have just identified this, and then we can assume without a marker, we can assume that there are more blank spaces here. That's one option, to assume that there are blank spaces there. That it may not be the case unless each time you write this, you move to the right and let's insert this. The insertion will be, and then move to the right and write a blank space, and then that's it. If we did this the last time, then now we don't know if these are blank spaces or not. You remember that sometime, particularly when we were speaking about stack, about push-down automata, we said that sometimes you are not sure what was there previously, kind of a malloc in C. That whenever you reserve memory, you are not sure what was there previously. So maybe we can more realistically assume that the Turing machine tape had something different here. So if we insert this part here, then we are ensuring that every time we write a symbol, let's say this X, then move to the right and write this, and then go back to this, go back to this. This is the addition we are doing here. And then we will just move not just to the first blank space, but to the second blank space. With this addition, our machine will work. I will draw again the machine so that it gets clearer for you. So the first thing says move to the right, then you have an X or a Y, which will be in turn omega. And then write an asterisk, move to the right until you find a blank space, move to the right again until you find a blank space, write the omega you are carrying, and then at this point, move to the right again and write a blank space, and then move to the left and find the previous blank space, and then move to the left and find the previous asterisk. Then write omega again in order to reconstruct the previously seen symbol, and then go back to the previous omega, to the previous R, sorry. Okay, so let's do another run for this machine. So we have, let me copy also this. It was X, Y, X, X, Y, and we want to copy it here. That's it. Then we start again. Then move to the right. This is the first thing we do. Move to the right. Here we have omega equals X, and then write an asterisk. If we write an asterisk, then we move to the right until we find a blank space, which is this part here. And then move to the right until you find the next blank space, which is exactly to the right of this. Here we write X because this is our omega. And then we erase this and write omega, which is X for this case. Then we move to the right again, which is this blank space. And then move once more. And then write a blank space there, which is already written, but just in case it was not a blank space. Then move to the left and find the first blank space. Maybe you will ask, well, I have a blank space here, but remember that it will find the first blank space to the left, which is not the one that you are standing on. Then you will move to this part here, okay? And then we have moved over there, and then find the asterisk here to the left, which is this one. We will go to this place, and then here write omega, which is the X. Then we erase this and then write an X. And we have finished up to this part. Then we go back and move to the right, meaning we are now standing on the Y. And I think this time it will work properly. So let's do just another iteration, because otherwise we will be doing these operations all the class long and it will be very boring. So the idea is not to get bored. So last time, let's take this Y, and then what does it say? Now omega will have the value of Y. Okay, then write an asterisk over it. So we temporarily destroy it, and then move to the right, and until you find a blank space, and that's it here. And then again, move to the right until you find a blank space, which is this one. And then at this point, move to the right. No, at this point, write omega, which is precisely this Y we are carrying here. we write the y, and then move to the right again. So we'll be here and then write a blank space, which is already written, but just in case, because there might be something different. Then move to the left until you find the first blank space to the left, and then look for the asterisk. And then we look for the asterisk. And there, reconstruct this y. At this point, erase this and write a y. And then we are here at this point, we go back and move to the right here. That's it. And you can see when we reach, for example, when we finished doing this copy, let's suppose we have already copied x, y, x, x, y, and there are blank spaces. We go back to this part. Let's suppose this is the asterisk, and let's see how this machine stops. We are supposed to have y as omega, and we have just written here our last y here. Move to the right, and then at this point, write a white space. Yes, we are executing here. Move to the left and find the first blank space you can find here, and then find the last asterisk or the previous asterisk to the left, which is this one. At this point, write omega, which is y. We are standing here, and then go back up to this part. At this point, move to the right, and you will find a blank space. What will happen here? Please tell me. We are in this state, and we are. Right. Why? Because we are telling the machine what to do if we have an X or a Y, but we're not telling it what to do if it finds a white space. So it's like there's an implicit white space here and then halt. Remember that for everything that is not explicitly stated, the machine will just stop. And then it stops. It has successfully copied the string from here to here. So that's how we designed this machine. Probably you did the same for homework when you needed to write the same string the reverse way. And then I want you to tell me as well, what is the language this machine accepts? Can we say this machine accepts a certain language?
I think that is XY clean star. So I mean, it's and Y is the alphabet, and the alphabet is clean star, I think.
Yes. Okay. Yeah. Right. This is better stated. Thank you. So yeah, the language is everything. Why? Because it will copy anything. And yes, we can say it kind of accepts a language because it will just do this kind of operation for anything that is here. And as a side effect, it will copy it. However, it will stop after having analyzed the whole string, and then it will halt always. So that's why it accepts anything. Okay, now with the clean star, remember that comes a great responsibility. With the clean star, great responsibility comes because we need to check always for the lambda string. So what would happen with the lambda string in this case? Do you think it will accept, or can we say the lambda string is accepted or not? How would you represent it? You say no. I didn't identify who spoke, but the mysterious voice said no. Okay.
I say this.
Okay, thank you, Emilio. The mysterious voice is solved. Well, let's see. Let's work it. Let's suppose we have the lambda string. How can we represent the lambda string in terms of a Turing machine? Well, just something like this, because you are standing as before, just before the string comes and then the string ends. So this is the representation of the lambda string. Then we start the machine. The machine says move to the right and then halt. So has the machine processed the whole string? Yes. Has the machine halted? Yes. Therefore, yes, it accepts the lambda string. So we ask these kind of questions because it's very important to be aware of what does it mean for a Turing machine to accept a string or not. Miguel, please.
¿Qué pasa si en el último, ay, no sé cómo se llama, bueno, en el último triángulo hay, nuestra cadena tiene algo más? O sea, por ejemplo, porque la sobrescribe, ¿no?
Sí, o sea, te refieres a si después de aquí hay otra cosa ya previamente escrita, si va a funcionar copiar o no.
Ajá.
Ah, ok, precisamente para eso lo sobrescribe. Vamos a analizar ese caso. So the question is, what happens if there is something else or something written previously on our tape? So let's do this example. I'm taking away this machine and taking it to the next page. So if I understand properly, Miguel is asking us what happens if we try to copy something like here and we have already y, y, x, y. Something like this, right? This is the question. ¿Esta es tu pregunta, Miguel?
Sí.
Okay, so let's execute this. Let's see what happens. We are standing here at this point, and then the first thing we do is move to the right. We move our head to the right, and we have an x, and thus omega is x. And then we write an asterisk over there. We write an asterisk, and then find the first blank space, which is this one, and then find the and then move to the, oh, it's not working properly. You're right. And then it says move to the second blank space, right? And the first time it won't work properly because what it will do is move this and then move until this part. And here it will write X. And then we will start doing stupid things with this machine because now we are standing here and then it says move to the right and then write a white space on it. And now that we are here, then go back to the previous white space, which is this one, and move to here, and then reconstruct the X. So yes, as you can see, this machine is not working properly. So I will let you this as an exercise now for you to fix this machine. As a hint, what you need to do is just here, before starting the operation of this machine, you need to identify this kind of garbage. And then at least create something like this. And then you can go back for normal execution. So at least you need 2 white spaces and then everything will work as before. And you can try to fix this. Emilio, please.
I have a question. What happens
Yes.
if in the first state of a machine we have 2 blank space? For example, it's blank space, and x, y, y, y.
And we are standing here?
Yes.
it will halt because it will assume that the string you are trying to copy is this one. And without this fix, this will also fail, because if your input string is lambda, then you need to copy here lambda as well. So the result should be, this is input, and the output should be this, and then again this at least, and then you can have any garbage you want. You don't care, but at least you have here lambda, and then you have a copy of lambda here, if you want to copy lambda properly. That's why you need to fix it here. So the fix is just a set of operations you will do on preparation for executing this machine.
Yeah, for the first one, I think it will work if we add an R delta, bueno, R de subíndice delta, luego se mueve a la derecha y se sobrescribe en delta. Y ya después se regresa, se hace un L subíndice delta 2 veces para regresar al delta de inicio.
Yo creo que es una sola vez, porque este de acá lo ignora. Acuérdate que ignora en el que está parado.
Ah, pero tiene uno antes, porque tendríamos 2.
Ah, este.
Sí, serían 2. Yo también lo tengo con 2.
De acuerdo. Okay, thank you. Thank you very much. Yeah, I think that's a magical command you need at the beginning, which says rara lala. And that's the command we need to prepare our tape. Now let's try the same example we had here before. So I will erase some things. And let's see what happens now with this fix. So we will include this fix as part of the machine. Here. And of course, we need the start here. That's it. Okay, so let's execute this. We will have this on preparation. Remember that we are standing here. We start the execution of our machine with the head on this position. Then we move to the first blank space to the right. And that is this one here. Then we continue the execution and then move one more space to the right, meaning that we are standing here. At this point, we write a blank space, which is this one. So we write a blank space here. And then, as you properly say, then we find the first white space to the left, which is this one. And then again, we find the first blank space to the left. That's it. We are back to the start, back to the beginning. And now we have ensured that we have here space for working, no matter what there is here. So as we said before, this is garbage, but we don't care. But we don't care. Yeah, there is always a feeling of discharge when you say, but we don't care. So you feel good, right? Well, but we do care for Turing machines. So it's not, we don't care for anything, just for garbage. We don't care for garbage in this case. Okay, so we have X and Y here. Let me change this because, okay, because I wasn't seeing all of you. Now I see all of you. Thank you. And now we are here. We can start our processing. We move to the right and we are standing here. And now we can say our omega is X, and then write an asterisk over there.
The image is frozen.
Yes. Yes, Camilo?
The image, your white background.
Oh, it's not moving.
Yeah.
But Okay, but it's not moving since like 2 hours. Meaning that I was just moving a lot of things since the beginning. Okay, now it's synchronized. Okay, sorry for that. So we have just written this asterisk, that is this one, then move to the right. We erase this and then move to the right, and then find the first blank space to the right. Sorry, it was not just move to the right, but find the first blank space to the right, and then again, find the first blank space to the right. Now we have it properly, and then we can write the X here. We erase this, and we write the X because this is omega. And let's see what happens now. And we write X, that is our omega, then move to the right, and then erase the garbage with a blank space. This is, and then move to the left, to the first blank space to the left, which is this one, and then find the asterisk, which is this one. Then we find this, and then, sorry, the asterisk, not the blank space. We find the asterisk and then write again omega, and omega is X. Then go back through this loop and move to the right again. We are here. And now we start here at this part, not here, but here. So we have omega is Y, and we write an asterisk over there. Then look for the first blank space to the right, then look for the second blank space to the left, which is this one. At this point, we write omega, which is Y. Move to the right, write a white space, and then find first the first white space to the left, which is this one, and then find the first asterisk to the left, which is this one. Then write omega again, and this omega will be Y, and then go back and move to the left. And then as we find a non-defined arc, then we halt. Okay, now this is working properly. So thank you, Miguel, for your question. Actually, this was a situation that we weren't prepared for, but now we have fixed our machine and it seems to work now for all the different possibilities. Okay. Well, so this machine is properly understood. And yeah, it accepts a language. Also, we didn't design for it particularly, but because it works for any string, then we can say effectively that the language that it accepts is the clean star of the alphabet, and the alphabet is XY. So I'm glad you have it clear, right? Okay, so let's go back to the part here where we have the two modes for accepting and not accepting a string. And I would like, before studying this again, I would like to design a machine that won't accept. For example, I want you to design a machine. Let me go back to this part. Design a machine, Turing machine, that accepts any string with 2x in it. No more, no less. So you can have some examples, being the simplest one, XX, And of course, you can add x together, and two x's. They can be not contiguous, meaning that you can do something like y, x, y, x, y, 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 x, y, 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 x, etc. Remember, then, when you are asked to accept or not a string, you cannot consider the blank space in the alphabet. So the alphabet will consist only of x and y, and blank space does not belong to the alphabet. The white space will belong to the machine's tape symbols, but not to the alphabet. And remember that the alphabet has to do with the language. These two are connected. Okay, so please design a machine like this in your notebooks, and when you are done, please show it to me. Yes, Abraham? Okay, let me try to copy what you did. You have no start, so on principle, that's wrong. So draw your start symbol, please, and then we will check it. I think the rest is okay, but this is for you not to forget this start line. This is very, very important. Oscar? Okay, let me copy the one of Oscar and then I'll copy the one of Abram. I think both of them are very similar. So we find Y's, then an X, and keep going to the right. Then we have Y, and finally we have an X, and then you keep reading for the Y's so that you don't accept it if it finishes with Y's. Thank you, Oscar. Now let's see this one. And now I will compare them. Abram, please.
It's the same. Just
no,
only two.
Not the same.
No,
It's not the
let me
same.
check.
No,
Okay.
no, that's not the one. It's the other one.
Okay.
The one to the right. Move your. Yeah,
I'm sorry. This is
one.
one. Sorry.
Yeah. Okay. Okay. So it's almost the same, but there is a small detail over there that that is important that you take into account. That's it. Okay. Thank you. So we will. I don't know if Cesar wants to show his as well. Okay, so yours is like the previous one, RX, RX. You have even one iteration more, so let me copy it because I like long Turing machines. So R, Y, and then X, and then more R, and then Y, and then more X, and then R. Okay, thank you, Cesar. So, well, we have some variants here. I think these three machines do different things. Maybe if we sort them from the shortest to the longest one, we should move this here and this here, okay? Okay, so if we check this one, that is the shortest one, we can see that we will start moving to the right, no matter what is it there. And maybe that's a small problem because let's suppose we have something like X and then X. The machine should stop here because there is already one X and then another X. However, because we are starting by moving to the right, we are just ignoring the first one because we don't know what it is. No, not true. Oh my God, what is this doing? This is taking screenshots as crazy. Give me a second. It has become alive. And now it's okay. Can you see my screen?
Yes.
Because I cannot.
Desktop.
You can see all my desktop. Okay,
Okay.
So let me share again this. Sharing. Good, now you can see. And what's the wood one? This one. Okay, sorry for the interruption. Okay, so, well, I was telling lies before starting because let's remember that we start reading our string on the previous blank space. So if we have something like XYX, we will have a configuration like this one. Okay, so we move to the right and we don't miss anything. So let's see if this machine accepts XYX. We move to the right, then we are standing here, and then if it's an X, we move to the right, and we are here, and we just pass this Y, move to the right, and then because we have an X, then we stop. So we are appropriately recognizing to X. In the second machine, we will be reading. Let's execute it again. We will start here and then move to the right. We move to the right, then we have this X, and then move to the right. Then move to the right. And we are here, and we just loop onto this Y, move to the right, and then we have an X, and this says move to the right again. And then we have a Y, and then because we have a blank space, then we will stop and accept this string as well. So for this string, the first two machines are accepting it. For the third machine, however, it won't accept this because it will be requiring a third X.
Sorry for the interruption, but yes. I was missing in the last R. There's a loop for every. It's like an error. Like if you find another X, then it will loop infinitely.
Okay. Well, that's important.
Yes.
Meaning that this is like the previously pitfall, right? Okay, then you have X, any Ys, and then you can have more Ys, and then find the second X, and then read more Ys. And if at certain point you find a third X, then you will loop, and that's correct. And also the machine needs the correction that also if at any point you find blank spaces, then you need to loop, because the only way you should stop is when you have reached the two X's here. So if we visualize the part that is not written here, then it means that at this point, this is the implicit part. Let me put a different color, a more different color. So we have here, and then we have a blank space here because we have finished the machine and the string correctly. And then we can halt, and this will be the only way for accepting it. What happens if at this point, for example, here you find a blank space, then you should loop because this shouldn't be accepted. What happens if at this point you find a blank space, you should loop. And what happens if at this point, well, here you are already looped. So this is very important, the looping mechanism, because this is not implicit, right? So maybe here what you need to pay special attention is that previously what was not explicit was the loop, this pit. Previously, when we were working with the DFA and with push-down automata, if we didn't draw this, automatically it kind of went to the loop, right, to the pit. And now whatever we don't say automatically goes to halt. So we have to think the reverse. That is why it is very important in all your solutions, including the first one, the second one, what to do when a different symbol is shown. And another thing that may be confusing you is this one, precisely that I'm telling you that the blank symbol does not belong to the alphabet. However, it does belong to the Turing's machine or the tape, or these are symbols for the tape. So whenever you think about this, maybe you will think, oh, because it doesn't belong to the alphabet, then I don't need to take this into account, right? So that may confuse you. That is why we are doing this exercise. However, it is very important always to state what will happen with blank spaces. At what point are blank spaces taken into consideration? Remember that blank spaces are taken as delimiters. So we are delimiting where our string starts and where it ends for accepting a string. So we move to the right, we skip the first blank space, and then we are looking or reading the string until the next white space. Afterwards, if we have found that our string has fails or does not comply with the specification, that is this one, then we need to loop. This is why this loop is very important. Actually, we can have just one loop. This helps for designing things maybe easier, I think. So I would say, okay, let's move this to this part, and you will have, okay, if you find an X or a white space, then loop, and then you can erase this part. Yeah, so it's just an equivalent, not that the previous machine was wrong. But as you can see, then if we do this, then the second machine and the third machine are very similar. Just that in this case, you are considering here this loop. And as for the first machine, well, we need to explicitly say or to differentiate that it will stop after the second X. Maybe here the rationale behind this was having an implicit X, then would lead to halt, which is okay. And maybe we need here a loop, something like this. And this looks strange. Okay, we need a loop here, and then we need to say with the white, let me see. No, we cannot fix it this way because it means that whenever it reaches the second X, it will ignore what comes afterwards. Let's suppose we have something like this. And this string should be accepted because it has exactly 2X. In the first solution, even if we try to fix it, we will have the first X. Okay, then we move to this part. And now we are accepting all Y's, and then move to the right. We accept this Y properly. And then when we finish this X, the second X, we will halt. Then the string will not be accepted because remember that there are two conditions. First, to halt, and second, read the whole string. And because we halted here, we have not yet read the whole string. This is why this solution needs to be to consider the second X, and then after the second X is read, to be able to read more Y's. This is very important until it finishes, until it reaches the white or the blank symbol. Yes. So finally, the answer that is complete is this one, because it considers not also these Y's, but also what happens when it finds a white space. And well, actually it should be just X, because if it finds a white space, then it's okay, it stops.
Teacher, I have a question.
Yes, please.
If in the first example, if we don't halt, so I replace with right delta.
Okay, I see. But under which conditions? Second X. You found the second X, and then you move to the right until you reach delta. Is it okay, Camilo?
Yes.
Okay. Yes. Yes, what you are trying to express here is that you find the first X after ignoring as many Y's as you have, and then ignore more Y's. And then when you find the second X, then what you want to do is just to find the end of string, right? However, this function, remember how R delta was written. And let me erase here so that I have a little more space. So remember that right delta was defined as move to the right while you can find more X or you can find more Y. The problem of using right delta here, this is too dark. The problem of using right delta here at this point is that you will be allowing to find more X, and you are allowed to have only 2. If we erase this, it's as if you had directly something like right, and then more x and more y. And the problem is that you accept 1x, 2x, and then 3, 4, 5, 10x. But yeah, but your way of thinking is correct. You say, okay, I have now I have the correct conditions, then I don't care. That solution is correct. For example, if you say with 2x, with at least 2x, then you don't care if you have 3, 4, 5 or more, then this solution is correct. You can add here r sub delta, and that's okay.
Okay, thank you.
I have a question.
Please.
What happened if instead of put r delta, we can put r negative x? That means that move to the right until you find something different to x.
Okay, I think that will work. Let us check it. So this is why questions are good, because they make us think. Okay, so Emilio is saying r not x. Move to the right until you find something that is not an x. So it will not stop because it will be looking. No, let me see. Let's erase here and do an example. And we have x, y, x, y, y, y. And we are standing here. Then we move to the right, and then we move to the right, and then we have the first x. Now we are here. And then we accept this y just by following the loop. And then move to the right. And then we have the second x. And then once we find this second x, it will move to the right until finding is different to x, thus stopping there. Because the condition is met, it will move to the right until it finds something that is different from x. So this is maybe this is not what we are looking for, because if we have here again, we cannot say the whole string is accepted. So maybe the only way for doing this is just when we have just found the second x, keep looking for a y, and if we find an x, then we know it won't work, and it will stop successfully only when it finds a blank space. It seems maybe there is no machine so specific for this previously defined, trying to reuse these blocks. We need to define something special for this case. Okay.
Okay. Thanks.
Welcome. Okay. Now, I want to ask you something. You remember this language, right? This is the canonical example for accepting that was it's a language that a push-down automaton cannot accept, being n, belonging to the natural numbers. So what about this? Can we build a Turing machine that accepts this language? Is a phrase structure language. What do you think? How would you proceed to answer this question?
I think yes, but we need like a kind of a counter, like
Mm,
I think we can do it without
like an
counter.
accumulator or something like that.
We need
So
some
you
sort
think
of
it's possible?
some sort of marker. Then we can compare like x's and y's, so they have the equal amount. Then compare y's and z's and t's. So I think we can do it.
I think as well. Maybe you can get some inspiration from the from the previous exercise, the one that we analyzed, and remember that it was a destructive method. Do you remember? So instead of counting them somewhere, whenever we found it, we just destroyed it. So maybe the procedure could be extended for allowing it, for doing it once more. Something like this. How would you change it so that you could consider not only X, Y, and Z, but also T?
And how about we replace, for example, the first x with I don't know, the blank symbol, then move to the first y, remove it with the blank symbol, then move to the first z, and so on. And then return to the beginning if we, of course, found each of these symbols. And then do it again, again.
Yeah, so you would have something like for the string XX, and YY, Z, and then you will start by destroying something like this, right?
Mm-hmm.
And then finally, this. Yes, but then after this, you would need to do some mechanism to travel from the original and to the last one, just to ensure that all of them were properly changed into blank spaces. In this case, instead of changing for blank spaces, what we are doing here is just doing a shift left, which destroys, but also does a shift. And this shift is very useful because once you shift this, you eliminate it, but you are reducing the string so that at the end, you have only two blank spaces together. And the first one was marked with a hash symbol. So yeah, this is the method for accepting this language actually. So this machine accepts this language, and then you just need to do some small modification to it in order to allow for an additional symbol, which is T afterwards.
So the idea is to add a new search for the T symbol, no? Like the Y and X.
Right. So if, maybe we can do it all together because it's, let me see if I can take this away. Copy. And we will try to pass it as small. We have just passed this like 100 times. But I think it's even worse when we do it on the real whiteboard, because we need to draw this a lot of many times. Okay, so we will start the same. Actually, I will just start copying all this. This is the backbone, this part, because we start recognizing X. Sorry. No. Okay, we are start recognizing X, then shift left, then Y, then shift left, then Z, then shift left, and we will just add another one because we are trying to accept T, exactly the number of times, the same number of times. And after recognizing T, then we can do a shift left, and then everything will go the same. We will just move to the left and see if we can find the hash. This is the backbone, which actually is this part. I'm just adding the T part so that we can process it. Okay, so the upper part will just come out from the last shift left, and it would be for everything that is white space, and go to the left until you find the hash symbol. And we will go back up to this part with the R, which is this one. I would fail the technical drawing if I study that. Okay, so let's continue. And here we have some things falling down, and now we need to take into account also T. For all cases where it should fail, if we find a T at the beginning, it's wrong. We cannot start a string with a T, with a Y or a Z. And then we use the pit. This will be our pit. For a shift left, after we shift left the several X, we shouldn't find any blank space, Z or T, because the only thing we can find after we have just shift left an X is a Y, which is correct, or more X is the only thing we can find. And as long as we find X, then it is correct. We just skip them and we will count them afterwards. When we finish a Y, then we can continue our procedure. But if we find here something that is different to that, which is a Z or a T, a Z, a blank space, or a T, then we go to the pit as well. For this one also, if after doing the shift left of a Y, we can find only a Z or a Y. If we find more Ys, then we can just skip them. With Ys is the only thing we can find until we find a Z. Here we find a Z. No, sorry, what I'm doing. X, Y. Or here until we find a Z here. But if we find here an X or a Y. No, or a white space. Or a T, then go to the loop. And here the same, X, blank space, or T. That's it. And then the new part says, if we find here more Z, then it's okay. We just skip them. It's not Z, it's T. Let me see. Why? No, yeah, it's Z. If we find more Z's, we skip them until we find a T. And if we find something different, such as X or a Y, then, or a white space, then we go to the bit. And finally, here, after doing shift left of a T, we shouldn't see an X, Y, or a white space. And at the end, this is the same as before. This is not no hash. And this is it. As you can see, the procedure consists on first shifting or skipping all the X's in this part, and then we continue shifting all the Y's, and finally, with the newly added one, the Z's until we find the T, and we will keep shifting this. And now the backbone of this goes X, Y, Z, T. Why do we do this? Well, because I want to show you that you can extend this procedure to accept just X, N, Y, N, Z, N, T, N, W, N, K, N, etc. with N belonging to natural numbers. And you can continue adding more and more here. And why this is important, because you remember the difference between X and Y n. This was crucial because this was not possible to do for a regular language, for a deterministic finite automaton. And then we found that it was possible with a push-down automaton. And then we found that just adding a new one was not possible for a push-down automaton. Then one is inclined to think that if we add one more, then it won't be acceptable by a Turing machine, right? But the thing is that these two languages are acceptable by a Turing machine. Well, the first one as well, but this one is the less powerful machine that can accept it is a push-down automaton. With this, now we know that we can continue adding more and more and more and more. And we are able to count them because we are just following a procedure that makes this possible, right? So this is the point for this. Yes.
In the last shift left, the final line is necessary, or
here?
It's just the second red line to go down.
This.
It's in the previous one.
No, I think this is okay, but this no. Okay. Sorry, my mistake. Thank you. As some teacher says, that's because I want to be sure that you are paying attention. Then I know you are paying attention, and that makes me happy. So we have a question from Emilio.
Okay, I have a question. I will say this in Spanish.
Yeah, it's okay.
Había leído que un lenguaje que contenga un número finito de cadenas puede ser decidible por una máquina de Turing. Pero en este caso, este lenguaje puede tener puede tener un número infinito, tal vez contable, de cadenas, pero no finito. Entonces mi pregunta es, ¿es decidible o no es decidible?
Yes. Well, Emilio is asking if this language is decidable. So first, let's go into this, because that's one of the main points I want to address in the class of today. So let's take the two languages. I'm erasing this one. So first we have this language, xn, yn, zn, and belongs to natural numbers. And that corresponds to this machine. So if we ask, is this language decidable? First, we need to define properly what decidable means. Decidable means that there is a machine that accepts, exists. There is a machine so that the language of this machine, yes, so the language of this machine, let's put this language A. So the language of this machine is language A. And this is very important, there exists another machine, let's call this machine A, and there is another machine B, whose language of machine B is the complement of language A. So you will say here, oh my God, why is the teacher making our life complicated? Because it was so easy, decidable. Well, decidable implies this. Decidable implies that there's a machine, it doesn't matter if it's A or B, it's just a name, that accepts the language. And also there is another machine that accepts the complement of this language. This means that it's decidable. Why decidable? Because decidable means that there is a machine that will stop when there is a string that is accepted and will stop when there is a string that is not accepted. So in order to maybe we can move this into another screen. Oh, I think I won't be able to do so. I'll maybe reduce this. Give me a second. I need space. Okay. Okay, so now we have plenty of space. So as you recall, previously we did something special with this machine. We changed or we modified some parts. We were doing this on the book, if you remember. And we say, well, what if I want this machine to say yes whenever it accepts a string, instead of putting halt here we did something that said, okay, now let's now we are on a hash, then replace it by a white space, move to the right and say yes, move to the right and say space. And if instead of just going and never stopping, then we can modify this machine so that it will do something that says, okay, then go and look for the hash, write a white space, say no, move to the right, say no, move to the right, and write a white space. So please pay attention what we are doing here. We are changing this machine so that instead of running forever, the machine will stop saying no. And here, as before, it will stop saying yes. So in both cases, this machine will stop. This is the key point. Remember that usually for a Turing machine, we say, if it stops and reads the whole string, the string is accepted. If the Turing machine never stops, then the string is not accepted. That's that means to accept a string. Then to accept a language, we said this before. 1, we need to halt, and 2, have read the whole string. This is what we said before. This means to accept. To not accept, we can have two options: never stop, or stop before reading the whole string. Yes. So this means to accept. What that is different than to decide. Certain language, L, can be acceptable, and if it's acceptable, can be decidable or non-decidable, or can be non-acceptable by Turing machines. So if we have this language, which is language A, at this point, let me change color. At this point, we know it's acceptable up to this point. If we check if there is a machine that can accept its complement as well, and the complement means all the strings that are not in this language, then we can say it's decidable. If there is a machine, or if we can only accept this language, but you cannot accept the complement of this language, then the language will be non-decidable. So usually we get confused with decidability and acceptability. And well, I need to explain all this because the question was on decidable languages. So far, all the languages we have been studying are decidable because we have not seen yet any language that is non-acceptable. We will see that next Tuesday. And it has to do with the paradoxes that we saw last class, you remember? So that's an example of non-acceptable language. When you ask a Turing machine something like, accept a Turing machine that cannot be accepted, that cannot be implemented, something like that. But we will formalize this, or we will see an example of this. Okay, so this language we have here, there is a machine that accepts this language. Let me put it even more concretely. We have, again, let me copy this. Copy, copy. Cannot copy. Don't despair. Copy. Okay. So, okay, so there is this machine that accepts the language X n times, Y n times, Z n times. We know this because we have seen it like 100 times. So this is the machine corresponding to this language. Now, what is the complement of this language? The complement of this language is this is the clean star of the alphabet. In this case, the alphabet is X and Y and Z minus the original L. If we call this all LA, just for future reference purposes, then the complement of LA will be the clean star of this minus LA. What does this mean? That it will just accept all the strings that are not accepted in this case. If I ask you, draw a machine that accepts the complement of LA, could you do this? Write a Turing machine that accepts the complement of LA.
I think that in order to draw or design a Turing machine that accept the complement language, only we remove the order of X, Y, and Z and put in different order.
Well, that's a hypothesis. However, you would need to draw, let's see, what you are saying is like start from a backbone that considers Y, X, Z, for example. But you will also need to consider all permutation X, Z, Y, or even starting with Z, X, Y, or starting with Y. No, that is already done. Or what about, oh, what about X? No, it's only XYZ. Well, maybe not so many differences, but for each one of these backbones, you will need to program all this. So there is a simpler way. Try to think a little bit more.
Do you remember
Okay.
the last step that you did with the yes and no? Changing
Exactly,
the no to the yes and the yes to the no.
Well, yes. Let's not complicate it yet with the yes and no. Let's just consider this machine and reverse the work, the way it's working. So that's the way the answer is aimed at. Oh. Okay, let me see if I can duplicate it. Yes. So now we have two of these on a single screen. So poor of you, I'm going to make you crazy and you will dream with this. Okay, yes. So in order to do this, let me make more space. Okay, so if we just change this, and instead of moving to the right and then looping, then we can say, okay, now move to the last white space and then stop. And in the other case, if instead of doing left, and if we find a hash, then loop. And that's it. This is the machine that accepts the complement of this language. This accepts LA and this accepts LA complement. Like it was kind of simple. So now we know that there is a machine that accepts LA and there is another machine that accepts the complement of LA. Therefore, LA is decidable. LA is acceptable. And because this machine exists, then LA is decidable as well. This is the proof for a language to be decidable, right? And when a language is decidable, then we are able to build combined machines that in a single machine, you have both yes and no. And that will happen only for decidable languages. If you have a language that is not decidable, you cannot do this. Why? Because there is no way you can make it to stop instead of looping. Yes? Or so. This must be very, very clear. So I will write it again.
So in the same machine, we have to, we can write the two possibilities, the complement and the original language.
That's the consequence of decidability, yes. But the definition of decidability is just this one. Let me write it here again. If there is, well, if there is a machine A, so that language of machine A is LA, and there is another machine B whose language of machine B is the complement of language A, then language A is decidable. And here for this example, this would be machine A, and this is machine B, and this is language A. Oh, that's invisible. And this is language A. The complement of language A is this one. And then a consequence of this is that you can combine both machines in a single one. But that is not the important part. It's just a consequence. The very important part is that you understand that when you want to say that a language is decidable by Turing machines, there is a machine that accepts this language, and there is another machine that accepts the complement of this language. This is the key point.
Okay, I understand.
Because this has no.
I cannot hear you.
So. Okay, I see. What about now? Can you hear me?
Yes.
Okay, yeah, sorry. My battery is finished because I have been in meetings since early, so they are tired, but not me. Okay, so is this clear, the decidability?
Okay. Yes.
Okay, but I have not answered the question of Emilio fully, because he asked several things. I didn't take note of it, but he also said there's a property that says all finite languages are decidable. And he asks, is this true? And we can say yes. And we can say this with ease. I mean, no, this is not a very difficult question to ask, because fortunately we know that all finite languages are regular. And because these are regular languages, they can be processed by a deterministic finite automaton. And do you remember the procedure for a DFA to change it to accept the complement of its language? So this is very ancient knowledge even for you, because we saw this like 3 months ago, and probably you don't remember. It was pretty easy. Let's remember, let's say we have some X and Y, and we accept X and Y. So the only string will be X and Y of this machine. And if I asked you to do the complement of this language, I know, so sorry, this is wrong. the language is XY. That's it. The alphabet is X, comma, Y. Okay, now it's properly written. If we ask for a machine for the complement of this language, it was so easy because we needed only to first to make explicit the PIT. So for this, the PIT is, because Y is not defined, it goes to the PIT. Because X is not defined, it goes to the PIT. And then X and Y are not defined here. And then the PIT, oh, is never acceptable, is X and Y. Now that we have done the PIT explicit, maybe it's easier if I copy this. In order to build the complement of this, the procedure says, well, it's pretty easy. You just change into acceptable states those that were not acceptable, including the PIT, and this is very important, and those that were acceptable states, now they become non-acceptable states. So you see, this is a very straightforward and a very easy way of finding the complement of this language, right? And because we have this very easy procedure and we can guarantee that we can always accept the complement of a language, given it's a regular language, and because finite languages are regular languages, then we can say that all finite languages are decidable. Yes? So let's remember, to say that the language is decidable, we must prove that there is a machine that accepts, let's say the language M accepts, M1 accepts L, and there is an M2 accepts the complement of this language. Then, if we are talking about finite languages, then we are talking about regular languages, because all regular language, all finite languages are regular languages. We know that. Because they are finite, then we can just build a deterministic finite automaton that lists all the different possibilities. And we can do that. Even if we have 1 million strings on this finite language, then we can use a 1 million states automaton, even if it's very large, but it can accept it because it's finite. So all finite languages are regular languages. We can process them with a deterministic finite automaton. So this we already know from before. As an example, we have this DFA that accepts X and Y. And if we ask, can we accept the complement of this language? Then the answer is yes, because for every DFA, we can build another DFA that accepts the complement of its language by just doing a very simple procedure. And this procedure is change every non-accept state into an accept state, and vice versa. Change all accept state into non-accept state, including those corresponding to the PIT. So there is a procedure for DFAs for accepting the complement of any regular language. So we can accept the regular language as well as every complement or as the complement of any regular language. Then we can say there is a machine that accepts the language and there is another machine that accepts its complement. Therefore, finite languages are decidable. So this is the way to demonstrate it, because we are relying on facts that we know or properties that we know on this on these kind of languages. Yes? Or why is it so awful? Because I see your faces like, why? Why you do this to us? It was not me, it was Emilio. He asked first. Well, anyway, we need to study this part. It's very important, and this property is also important. And also, going to another part of this question, it's very important to know about, Emilio also taught about countable and non-countable. So now I want you to tell me first, and also let me put a screenshot for you. It is the Chomsky's hierarchy. This is also known as Chomsky's egg because it looks like an egg. Oh, not properly copied. I don't know why it's so complex just to copy and paste a bunch of bits, and it's like they are transferring through Bluetooth or something, like very slow. We say the bits are crawling, like, okay, but now they have reached their destination. Okay, so we have studied regular languages. Remember, this is the Chomsky's egg we have been studying since the beginning of this course. So we have seen regular languages accepted by finite automata. We write them as DFA. Also context-free languages that are accepted by push-down automata, and we have studied them properly. And we have also phrase structured language, which are accepted by Turing machines. That is our subject now. Maybe we can write it as Turing machines. So this is the Chomsky's hierarchy. So if you have a finite language, you can be sure that it's a regular language. It doesn't mean that all regular languages are finite. Why? Because if I write something like X asterisk, is this a finite language? No, right? Because it has an infinite number of strings. However, can be accepted by a finite state machine?
Yes.
Yes. So is this a finite language? No. Can be accepted by a finite state machine? The answer is yes. Why? Because we know we can do a DFA, and a particularity of all these machines is that all of them have a finite number of states, all of them. And this is a very important property. Maybe the tape is infinite, maybe the stack is infinite, but the number of states they can be on is finite, always, always. Okay, so this is an infinite language. We know that. And now, is this infinite language countable or uncountable? Remember
That's
that
countable.
Yes, yes, right. Remember that for saying it's countable, we need to establish a correspondence one-to-one with natural numbers. So in this case, we can just count the strings with length 0, with length 1, with length 3, 4, 5. Oh, I missed number 2, 2, 3, 4, 5, 6, etc. Yeah? And so this is very important. This is for an infinite countable. Okay, so just to finish answering the question, then yes, when we say all finite languages are decidable, and then we don't know about infinite languages, because there will be some infinite languages, of course, all of them countable, that are not decidable. So some of them. So we cannot say the same about infinite languages. And we are never dealing with uncountable languages. We cannot deal with